Alright, dear students, welcome to your Applications of Calculus series. We're going to have quite a number of videos on this, and I'm going to slowly show you a few things you need to know in Applications of Calculus. In this particular video, we are going to actually talk about the cubic functions and how to draw those ones. And you know what? I hope you enjoy this lesson. Alright. So let's quickly start with what we've got over here and see what we can do. Alright, so now that we have our applications of calculus over there, I hope you're taking in your notes as well, and then we'll be seeing what to do as we go. So with the cubic functions, I want you to be able to compare the cubic functions with the quadratic functions that you already know. Firstly, let me remind you that a quadratic function is more like this. We have it as ax squared plus bx plus c. That is what you learned when you did your quadratic functions. So the shapes of these graphs were affected by the a value. We knew that a0 smaller than 0, rather greater than 0 for this one, and smaller than 0 for that one. So what we knew was that if a happens to be positive, the graph will actually just smile. We will call it smiling, the concave up. It will be like this. So this is the shape we were expecting, and similarly we're expecting a shape like this when this a value here was negative. So the shape of these graphs were actually determined by this a value. So I want you to see the relationship now between the way we see the shapes of these graphs related to that a value. It's actually the same, except it's slightly different. I want you to look at it this way. Look at your cubic functions that I put here in advance for you. Well, a cubic function, now this is the general formula for a cubic function, where a, b, c, and d are all constants. So those will be any numbers, you can put any number there, and d, of course, will be the y-intercept of that function. So again, in this situation, the shape of the graph is determined by this a here, the coefficient of x cubed. So we are saying if a is greater than 0, that is if a is positive right here, the graph will first of all go up, so be the shape, go up, and then go up, like this. So this will be the shape that we'll be expecting right here if a is positive. So we expect just that shape all the time, up first, goes down later. So we have this type of a shape. And as you can see, I don't have to overemphasize things here. Notice we will be expecting a maximum of 3x intercepts. Okay? So I'm saying a maximum of 3x intercepts because you may find that at times the graph may be like, let me put it, let me try it again. Let's say the graph is like this. Here's a situation where you may have two. It's when the turning point is right on the x-axis. Say something of this sort. Say this was a graph of yours that you've got down here, and as you are seeing, the graph is resting on the x-axis. So when you calculate your x-intercepts, you will get that x-intercept, maybe x is equal to -1, and maybe you get x of 2 over there. So what it means is that this one is the one that will be repeating itself. So this is the time when you have 2 x-intercepts. There is a time again when you may actually just have one. Like for example, if I have a graph such as this one, at this point I'm just using when a is positive. Let's say that. As you can see, there is only one place where that graph is touching the x-axis, so we will have just one x-intercept. So it's the cubic functions, I say. As for the x-intercepts, we expect a maximum of 3. If I was talking about the quadratic a quadratic is x squared, the maximum power. We expect a maximum of 2x intercepts, and now with x cubed, we actually accept a maximum. We expect a maximum of 3x intercepts, isn't it? Maximum. So it means we can have less than that. Okay, so this is what we've got. So again, please notice if your A happens to be negative, your graph will go down first, get to the turning point, and then up. And notice this time around, we have two turning points actually. The one that is here at the bottom, which we're going to call the local minimum. That will be the name we're going to give it as the local minimum. And then we have that turning point, and that will be the local maximum. It's not the maximum y value that we can have, because this graph here is on like this, and it is on down here. It's just the local maximum for this graph and the local minimum. So in this graph here on the right-hand side, this one will be a local minimum, and that one will be a local maximum. So it's important to actually grasp the concept, or this concept, to see when A is smaller than 0, what happens. When A is greater than 0, what happens. So that's the first skill you must have, okay? Keep these shapes in mind. Before I go, maybe you just expect this shapes here of graphs. Apparently, we also have these type of shapes here. Just to check the side, your right hand side here. So these are also cubic functions, and these are also the type where you actually get one x-intercept. The shape will be something just of that sort. If you remember the graph of x cubed, it's just like this, isn't it? So even the graph of negative x cubed, if you remember, it looks exactly like this one at the bottom. So this is we are going to talk about these type of graphs a little bit later. For now, we are interested in this part here, these ones that are over here, this type of graphs that we have over there. That's what we're going to talk about the most. Where we have two turning points, as you see, the local maximum and the local minimum. And we actually have to learn how to get those points. How do we get our x-intercept, and how do we get our turning points, which we call the local maximum and the local minimum. In fact, we're going to have to learn how to sketch these graphs today. Before I teach you how to sketch these graphs, I want you to understand what these knots here that I put here mean. Now, when we did calculus at the beginning, I told you that the first derivative was an expression for gradient, isn't it? It was an expression for gradient at any point on a curve. Okay? So what it means is that if your first derivative is negative at any point, it means even your gradient is also negative, isn't it? So if your gradient is negative, you expect the function or the tangent you draw at that point to be slant to the, let me just say slant to the left. If this is how your marks are going from here down like this, we say they are decreasing. Your performance, you're not improving at all, is decreasing. So that is when we say, if your gradient is negative, we say that a function itself is decreasing. So for example here, if I am asked to draw a tangent at this point on this graph that I've left with green, you can see that it is at this point that the tangent will be slant to the left. And even at that point, the tangent I may draw will be slant to the left. So all this time, we say that the first derivative, or the gradient, happens to be smaller than 0. It's negative. It's not exactly the main purpose of this lesson, but it's important to know. Look, if I draw a tangent there, do you see that it's slant to the right? And here it's slant to the right, meaning that the first derivative at those x values, meaning from this x value here backwards, it means the gradient will be positive. In between that this x value here and that x value, you can see how the graph is slanted to the left. So since it's slanted to the left, even at this point, the first derivative is smaller than 0. But there is a full lesson when I explain why this is important to remember. But for today, let's dive into the sketching of these graphs. Well, there are a few rules I want you to know before we start sketching. That we follow a few guidelines. So here, if you need the notes, quickly check these ones that I have for you here. Notice how we are going to do this. When we're sketching the cubic graphs, I firstly want you to get the intercepts. Okay, that is the y-intercept and the x-intercept. Luckily for us, we already know that if we ever want the y-intercept, we just have to make x 0. That's all we do. That's the easiest part right there. So I already have a function that I pulled out right here. So whenever I say something, we will do it on that function. So for example, if I ask you now to give me the y-intercept of this function, all you need to do is to go and put 0 wherever there is x. So there will be a 0 there, 0 there, 0 there. And as you can see, your y value you will get will simply be negative 20. So we are expecting 0 and negative 20 to be the y-intercept of this function. Very simple. Like I said, the d value, this last value here, is always the y-intercept. And secondly, I want us to now calculate the x-intercept. Now, for the x-intercepts now, people, we have to remember the polynomials that we learned. Okay, I taught you how to factorize here. So the x-intercept, you just make sure that you make y 0. In this situation, let's just call our y function of x. We can see that in place of y, there is function of x. So to be able to solve this, the equation which says function of x is equal to 0, you may have to first of all factorize function of x. So what I want you to do is to have this function right here, x cubed minus 9x squared, is that plus 24x and then minus 20. So this function, to factorize it, if you check your polynomial lesson video, it will be right there somewhere. So if you've got function, if you have that lesson run, if you watch it, you realize that I have asked you to find the x value that will give you a remainder of 0 if you substitute it everywhere here. The x value that will give you 0 here eventually when you substitute it is the one that I want. So I told you to use your trial and error. You try 1, if it doesn't work, you try negative 1, if it doesn't work, you try 2, if it doesn't work, you try negative 2. But luckily for us, in this particular sum, function of 2 will actually give us 0. Pause there and check if that is the case with your calculator as well. So since function of 2 is giving us a 0, we can easily say, well, therefore x minus 2 is a factor here. So factorizing a cubic function is no longer a problem for us, I hope. If it is, please watch the video I am referring to. So that is x minus 2 here. Well, to get to the second bracket, you have to express function of x, this whole thing, in terms of its own brackets when you factorize. So you ask yourself, what do you multiply x with so you can get x cubed? And as you can see, that should be x squared. And in the middle term, I say don't worry about it, just like bx. Then you ask yourself, what do you multiply negative 2 with so you can get negative 20? And I believe you said 10 over there. So that's how you get most terms in your second bracket. To now get your b value, we agreed that we just have to use the coefficient of x squared. And to do that, you find terms that will give you x squared when you multiply. And I say that will be that one and this one and that one. I say first and second, second and first. It's always like that for these ones. So you don't have to stress, it's always the case. So in this situation, you are seeing that if I multiply the first one, I'll get bx squared. and then I'll get minus 2x squared. I'll equate that to a term in the original function right here, which has got x squared. And I think you're noticing that is negative 9x squared. Right? So at this point, you equate the coefficients. You just take the coefficients. In case you forgot, let me just equate the coefficients here. Okay, so you're going to take b and negative 2 and equate that to negative 9. Carrying on, we can see that our b value is simply going to be negative 9 plus 2. That should be negative 7. So let's go and now fully factorize function of x. Okay, so we are going to substitute it back here, the b value. Okay, so I'll have x minus 2, and don't forget that one is now x squared minus 7x plus d, like this. And notice the second bracket can still factorize, so let's go and factorize it. What are those two numbers you're thinking of that will multiply to give you 10? When you add, you get negative 7. What are they? You are right, that's negative 5 and negative 2. Okay, so remember what we are solving for, huh? We are solving for function of x is equal to 0. We want to get the x-intercept. If you have forgotten, this is what we are solving for. Function of x is equal to 0. So in this situation, you put a 0 over there, and to solve for x, I think if we have 3 brackets like this, everyone can appreciate that x is equal to 2, or x is equal to 5, or x is equal to... Oh, it means x is equal to 2 twice. So, here is the thing. If you count the number of x-intercepts we've got, you will notice that we only have 2 x-intercepts. And I said that is a situation that arises if one of the x-intercepts happen to be a turning point as well. I'll show you how to sketch the situation we find ourselves in now. So this is how we get our x-intercepts. Let's keep this in mind. Let's keep our x-intercepts in mind, 2, twice, and 5. Then let's go and figure out what else I want you to be able to do. I want you to be able to get the turning points of this cubic function. And this is what you do. For turning points, or for stationary points of a function, all you need to do is to find the first derivative. This is the first derivative, and equate that one to 0. So let me remove that. I'm sure you'll be able to see it clearly how let's do it. So all you need to do to get the turning point is that you have to remember this is equal to 0. But maybe you may wonder why. Well, here is what I said. If we have a cubic function such as this, at this point, from this point backwards, we can see that the gradient is positive here. The graph is slant to the right, and the gradient is negative somewhere here. Again, it's positive over there. That's what the slope definitely is positive. But at a turning point, if you were to draw a tangent, it will have to be a horizontal line at a turning point. So what I said back then as well, or what you have to remember, is that the gradient at a turning point or of a horizontal line is equal to 0. So because the gradient of a horizontal line is equal to 0, from what you learned about tangent, the tangent has the same gradient as the function at the point of contact. So in this situation, that is why we are saying that the gradient of the function as well here at this point is also equal to 0. So remember, gradient is 0, it means the first derivative is also equal to 0, because the first derivative and gradient, I told you the relationship between these two. So that is why, if we want to get the turning point, we equate the first derivative to 0. So let's go ahead and do it for this particular graph. So I am going to actually do it the way I would expect you to do it. So You may find your first derivative first. Remember, the function I am deriving is actually to our left. This one right here. So please, we are deriving that function. Okay, so derive it. You should get 3x squared. Instead, negative, should be negative 18, right? Yes, and of course, that one will be plus 24. That should be simple. And then you say at stationary points or turning points, the first derivative is supposed to be equal to 0, like that. So what you have to solve now is this equation. That's what you solve. Simple. And notice how this, if you divide it by 3, 3 is a factor, isn't it here? So if 3 is a factor, so go ahead and divide by 3. You should get plus 8 here and say is equal to 0. As you can see, factorizing this one is going to be child's play. There is no need to stress here. So you put your x and your x. Two numbers you multiply to get 8. When you add, you get negative 6. Definitely negative 4 and actually, sorry, negative 2 as well. Yes, correct. So here your x is equal to 4 or your x is equal to 2. Well, those values that we just calculated over there are the x values of the turning points. You will need to also have the y value of the turning point. And from what you have, you just have to substitute the x value into the original, please, into the original equation. The problem is people may come and substitute these x values that we got here into the first derivative. No. You have to go and substitute it into the original, into function of x, which has not been derived. That's where you substitute. So that's how you get your y values. So to get your y values, you're going to have to say function of 4. What I mean by function of 4 is wherever there is x, go and put 4 in the original equation, which is again over here to your left. That is where we are substituting as the original equation. So I'm going to substitute x over there. As you can see, I am putting 4 wherever there is x. That should be easy to figure out. It's 24, then you put 4 wherever there is x. And the y value you should get when you do this, you need to use your calculator properly here. You should get negative 4. Well, I'm not going to waste your time and do the same for 2. Just know when I say function of 2, I mean substitute it into the original equation. And you will get 0 over there. So those are our turning points. The coordinates of our turning points are 2 and 0. And we also have 4 and negative 4. So keep these in mind, because now we would like to sketch this graph. Now for us to find it easy to sketch this graph, I may have to sketch it at a place where I can easily see my coordinates. So I am going to actually, let me take this with me. Take this along with us. That's the equation. Okay, so let's sketch this graph easily. I'm going to make space for it. We're going to try and sketch this cubic graph using the information that we have so far. The reason I wanted this function with us is because I wanted you to pick up the value of a. Firstly, at this point, notice your a is equal to 1. So if your a is equal to 1, it means we are expecting the graph to go up first and then this is the shape we're expecting. So we just have to figure out, and you see our turning points are at this point and at that point. So in this situation, we know that this will be 2 and 0 here, and this one here should be the one that is 4 and negative 4, because it's the one that's bigger. So there will be 4 here and negative 4, like this. And as we can see, what were our x-intercepts? We know that this point is also an x-intercept. So it means the x-axis is going like that. And that point, from what we have, should be 5 over there. So that is what we have. In fact, it's when you sketch it, it's still positive 2. It means the y-axis is somewhat over here. Like that. And if you remember, what is it that was our y-intercept here? And again, our y-intercept is actually just negative 20, so it is over there. So as you can see, I kind of just started by drawing the graph. Look, when the x-intercept repeats itself, like in this situation, x is equal to 2, x is equal to 2, that same x-intercept will be a turning point as well, which we can prove right here. We calculated the turning point to be also equal to 2 and 0. So this will be the graph that I'll be expecting you to have here, and that will be the graph. But as you can see, I started by drawing the curve itself. It will be maybe a little bit different if I start with the y-axis and the x-axis, just for the fun of it. Let's see how bad it can be to draw the graph properly. So we put our y-axis, we put our x-axis, we should have a bit of scale in our hands. We know that 2 is important to us, so I'm going to put 2 over there, and maybe 5 over there. And the y-intercept, we were told it was at negative 20. So what we have gathered is that this graph should turn at negative 2, and there was yet another turning point at 4. Okay, so it should be somewhat like this. Like that. Okay, you are going to be able to draw it anyway. This coordinate here is 4 and negative 4 in your hand. You can do that, and this one is negative 20. A bit of skill is required. So don't just say then, well, this is, if you see how where I put negative 4 and negative 20, it actually is questionable. I should put it a little bit lower, isn't it? You should have a scale in your fingers or in your pencil, or really just should be reasonable enough. Okay, so this is a cubic function already sketched and with all the critical points put in. There is one last point that you have to know about these cubic graphs, and that is the point of inflection. Notice this graph goes up, concave up, and there is that point over there where the graph will change. Rather, this was actually concave down for starters, and now this is concave up. So that point over here, we call it a point of inflection. So to get a point of inflection, all we need to do is to find the second derivative. Now, if you are failing to understand what I mean, let me show you your notes here, so you can pause for a second trying to understand it. So, if you have a point of inflection, at times, the functions that have 2 turning points, you may have to just calculate the point of inflection yourself. So you just find the second derivative, equate it to 0, it should be simple to find. So in this situation, if you want to find the second derivative, look, this is our first derivative, right? If I want the point of inflection for this particular graph, I would have to just say, let me find my second derivative. So second derivative is very simple to do, because all that's required of you is to really just derive this one again. So it will have two of those, and derive the first derivative. You should get 6x minus 18, like this. And then all you need to do is to equate it to 0. So this is what you will have. And of course, your 18 will come on the side, and notice how your x is going to be equal to 3. Very simple, really, if you ask me. So that is the x value of the point of inflection. So if you want the y value of the point of inflection, you still go and substitute into function of x, the original. Please just know that you have to always substitute into the original if you want to get the y value on this cubic graph. So this is what we've got over here. So let's rather carry on, since let me do that. And put that x is equal to 3 into the graph. Hope you still remember that one. So it makes sense, right? If your x is equal to 3 over here. So I always actually tell people that if you have two turning points like this, the point of inflection, we call it the point of inflection like this. This point of inflection happens to be the midpoint, actually. It's the midpoint. The midpoint of the turning points. So if you want to find the y value easily, you could say 0. You know, if you want the midpoint, you can say 0 plus negative 4 divided by 2. You should get negative 2 here. So it will be 3, and the y value is negative 2. Even if you say 2 plus 4 divided by 2, you should be able to get x of 3. So it doesn't matter how you do it, as long as you do it anyway. So yes, this is what you do. So now we are just going to have as many examples as possible, and then we're just going to carry on. So here we are. Let's carry on. And let's have some more sums. And I've got plenty of them. So it's the choice will be ours, really, as to which one we are going to do first. So since they're already arranged in this order, let me just help you by taking that one that is seemingly very simple. This one looks very simple to do, really. So if we have hx like that, I'm going to first of all get the x-intercept. If you want to find the x-intercept, you're going to have to make y0. But before you do that, factorize. So in this one, because x is a common factor, I'm going to take it out. There is no need for me to go through the pain of factorizing using those polynomial methods that I taught you. At this point, really hx can easily be factorized. So I'm going to put x there, and think of those two numbers we multiply to get 36. When we add, we get negative 12. It does look like it's x minus 6 and x minus 6 too. So if I put a 0 here, because we are solving for y, we want the y-intercept, this is what will happen. So x minus 6, x minus 6, we have again the x value repeating itself here. So x is equal to 0, or x is equal to 6 twice again. What it means now, if your x-intercept is repeating itself, it means it's also a turning point. So we already know what the turning point, one of the turning points is going to be here, really. So let's go and get that turning point. Okay, this was the step where we were finding our intercepts, the x-intercepts actually. Notice the y-intercept here is 0. Do you see that? If you put x of 0, you should get the y-intercept of 0. Okay, just so we can have space, I'm going to create space for us there. Well, if we want to find the turning points or the stationary points, writing that will take a long time. So if you want the turning point, what I said was, you derive the function first. Here is derived, and that is 3x squared, and that is minus 12 excuse me, that will be minus 24x. Okay, and secondly we'll say plus 36. This is the first derivative. So we have that is the first derivative here for this function that we're calling number 1 in our own exercise. So if we have that function as our first derivative, we know that at a turning point, your first derivative, which in this situation is that one, should be equal to 0. So yes, repeating that over and over again is a problem, but let's just go ahead and enjoy it. Alright, common factor, and you see there is 3 as a common factor here. So feel free to see that as well. And divide by 3. It should be negative 8x, and of course that one will be plus 12 is equal to 0. Factorizing these. How? Are you thinking of two numbers you multiply to get to 12? When you add, you get negative 6. I hope you are, so that will be your negative. Sorry, when you add, you get negative 8. You see, I'm already getting ahead of myself. So it should be negative 6 and negative to get to, it should be negative 2, isn't it? Yes, that should be correct. So as we are seeing here, if this is what we've got, our x values should be, in this situation, your x should be equal to 6, or your x is equal to 2. But what I said was, to get the y value, you go and substitute into the original equation. So go ahead, I'll try that as fast as I can to get this going. So let's find out what we will get over there. Okay, I am noticing function of 6 there will give us 0, and here function of 2 is giving us our 32. Okay. So that should be all that we've got here. Okay, so those are our turning points. We have our turning points, we have our x-intercepts. Sketching this graph should be simple for us to do. So let's do it properly for once. And this is going to be the turning points. Let's not forget it is 6 and 0, and we also have 2 and 32. 2 and 32. Let's put them there. Okay, let's put our y-axis. Let's put our x-axis. Our x-intercepts as x0, so we know that the graph will cut at this point, and it will cut at 6. In fact, it won't cut. It will actually touch at 6 because it's a turning point and an x-intercept, so it will touch at 6, and here it's at 0. And our turning points, there's 1 at 2, so somewhere here there should be a turning point, and maybe that high. So let's just assume that is where 32 is. So the graph should pass at that point. And from what we're gathering, since A is positive, the graph should go up first. So I'm assuming if I try to go up like that, and then come back properly, so I should rest at 6. Like that. I hope you have a better graph than mine. That's what I do. Ooh, just one curve, okay? For you, just draw one curve. Okay, so that is what we are expecting hx to be. This will be the shape I'm expecting from you, so you should find it easy to do. Again, if ever you want to find the point of inflection, which in this situation it will be over there, the point of inflection, you just do this, you get the second derivative, and I just need the first derivative. where is that label? Okay, I cannot see it now. So what I can do, because I don't want to do things, I'm going to get the first derivative real quick. That should be 3x squared minus 24x, okay, plus 36. If you derive it again, you should now get 6x minus 24. That should be what you get. And from what I said, you put 0 there and make sure that you correct like that. Okay? So if your 6x is equal to 24, your x should be easy to find. And 24 divided by 6 should be 4. So x is equal to 4 over there. Or you can calculate the midpoint of those two turning points. It's really your own thing. And don't forget, this turning point is the one that is 2 and 32. It's important to just make sure the critical points are shown on the graph. You don't want to leave that out. So this 6 and 0 is basically. So that's one function. I think you are getting the whole point now of how this is done. So I'm going to now carry on and give you a few more examples. Just carry on and then do your second lesson on this, where I will give you the homework. Well, in actual fact, do answer this question that we've got here. So please try to follow the few things that I told you and answer this question that we've got over there. I see there is one thing, your x is, that one is negative x cubed, so I think you'll be expecting the curve to look something of this sort. So go ahead and try it yourself, and we will definitely talk about it in our next few lessons. So, like I said here, I hope to see you soon. Okay, thank you.